Good day, everyone. Thank you for being here. My name is Lee. I'm a PhD candidate at UBC, and today I will be discussing an ongoing project on detection and diagnosis of ring formation in lime kilns. This work is co-sponsored by Can4 Pulp and Spartan Controls. I will not name everyone here, but I would like to acknowledge the help of my academic supervisors and industry collaborators. The focus of today's talk is on developing an indicator for ring formation. I will begin with some background information into the process and the available resources. I will then discuss our proposed approach for both the project generally and the development of the ring indicator specifically. Data preparation and visualization is described before presenting preliminary results from the ring formation indicator. Finally, I will provide some concluding thoughts and discuss our future ambitions. First, a brief background into our project. Lime kilns are long steel tubular reactors in the recovery circuit of kraft processes that can be over 100 meters long and over 4 meters in diameter. Generally, kilns are the most energy-intensive units in kraft pulp mills. Kilns are inclined at around 2 degrees and rotated by a drive gear to allow solids to move through the kiln. Wet lime mud enters the kiln where it dries into a powder and preheats before agglomerating into nodules that then undergo calcination, converting the calcium carbonate into calcium oxide and carbon dioxide. Calcium oxide nodules exit at the firing end of the kiln, where they are then used to regenerate white liquor. The figure on this slide illustrates a kiln that has been outfitted with thermal cameras to collect shell temperature measurements. Ring formation is described in literature as the most troublesome problem for lime kiln operation. A survey of Swedish kraft mills indicated that over 70% suffered from ring formation, and most did not know why. Rings can choke off a kiln, costing upwards of $50,000 per day in purchased lime, and in some bad cases, rings can cause damage to the shell or the refractory that can cost over $3 million per event. The figure presented here shows a firing end ring in the top left and a mid-kiln ring in the top right. The bottom photos show debris from a ring that has been partially removed by thermal stress fracturing. In this project, we are working with 3 primary resources to perform ring detection and diagnosis. The main resource is tabular time series data from the kiln and recost area that is taken from the process historian. A total of 60 variables are provided as hourly averages spanning over 5 years of operation. 30 of these variables come from thermal cameras, with 3 thermal cameras and 10 measurements each. The remaining 30 variables are relevant process variables such as flow rates and compositions. Another resource for this project is a collection of raw images taken every 4 hours from each thermal camera. An example of these raw images is presented on the right, where the measurement areas illustrate how the image is converted to tabular temperature data for storage in the historian. Finally, another important resource we have is the ability to communicate with engineers and mill personnel to provide insights and supplementary information. 24 of the 30 thermal camera variables are used to construct a shell temperature profile. The remaining 6 variables are omitted because they relate to exterior bracing. The 24 kiln shell temperature measurements correspond to specific positions along the length of the kiln denoted by their distance from the firing end of the kiln. The figure presented here provides a sample of the kiln shell temperature profile. Note that the shell temperature measurements that make up this profile are not equally spaced. Another thing to note is that the color of the squares indicate the measured temperature according to the color bar mapping shown on the left side of the figure. This project has 2 distinct objectives. The first objective is to detect ring formation, and the second objective is to diagnose potential causes. The first objective involves early onset identification of ring growth or decay combined with estimation of the extent and rate of ring formation. Successfully accomplishing this first objective can enable timely maintenance and prevent refractory damage. The second objective involves identifying factors that contribute to ring formation and using this information to determine improved operating policies. Ultimately, we would like to develop operating policies that mitigate ring formation and extend the time between unplanned shutdowns. Now I will present some more details about our proposed approach. The general strategy for this project involves the following three parts: commissioning, ring detection, and ring diagnosis. Commissioning the project involves acquiring the data and contextualizing it with process knowledge. Commissioning also includes preparing the data for subsequent analysis. This can involve data visualization, outlier removal, and other pre-processing tasks. The second part of our general strategy is the primary focus of today's presentation, and it involves ring detection. From a machine learning perspective, ring detection is akin to labeling our data. We have unlabeled time series data, and we would like to add labels where these labels indicate the formation of rings. As I will show later in this presentation, the raw thermal camera images can be used to validate our attempts at labeling the ring formation events. The final part of our strategy involves leveraging our labels to perform supervised learning and ultimately diagnose the causes of ring formation. Since the labels generated during ring detection will be correlated with relevant operating conditions for ring diagnosis, it is imperative that the ring detection is accurate and carefully validated. Our approach to ring detection involves generating residuals. Residuals are the difference between estimated and measured shell temperatures. A residual value is generated for each kiln shell temperature position, denoted by X, and each sample time, denoted by T. Consider a kiln that is operating at a relatively steady state with respect to the energy balance. In this case, high positive residuals potentially correspond to a higher than expected radial thermal resistance, while high negative residuals potentially correspond to a lower than expected radial thermal resistance. Whether the desired behavior is observed depends on how the estimated temperatures are generated. Currently, we're studying two different approaches to generate residuals. The first approach is used as a benchmark, and it involves some algebra combined with a priori process knowledge and clean reference profiles taken after a shutdown. The second approach relies on statistical forecasting of the kiln shell temperatures. Today I will be discussing the second approach. Once the residuals are created, the next step is to post-process the residuals to develop the ring formation indicator. While the residual may continue to reflect a persistent mismatch between the estimated and measured shell temperature, this is not desirable for our indicator. Instead, we would like the indicator to reflect the changes in the state of the ring. Therefore, one simple example of post-processing is to take the first difference of the residual such that the temperature mismatch is reflected in the indicator only when it changes. Additional post-processing activities can involve rolling averages, thresholding, and discretization to address noise. Finally, it is important to carefully validate the ring indicator with the raw camera images. Next, I will briefly describe some of the steps taken to visualize and prepare the data. One early challenge we had in this project was finding a way to intuitively visualize large quantities of kiln shell temperature profiles. The unequal spacing of the raw measurements contributed to this challenge. Effectively visualizing the data can help direct our attention to interesting periods of operation. It can also help us understand the quality of the data and the effects of data cleaning. The figure presented here shows the same profile as before, except now piecewise linear interpolation has been performed to address the unequally spaced measurements. The horizontal color bar at the bottom of this figure displays the same information as the line plot, except now the y-axis is embedded using a uniform sequential color mapping. If we take the horizontal color bar from the previous slide, rotate it 90 degrees, repeat this for every sample, and append them together, we get the spatiotemporal heat map shown here. The measurement position is shown on the y-axis and the date is shown on the x-axis. This approach allows us to intuitively visualize over 5 years of kiln shell temperature data. From the heat map, we can see events such as shutdowns, which are shown by the black vertical bands. We can also see extended periods with zero variability, where the camera is not operating correctly. Although it is not shown here, the visualization tool also includes a graph below the heat map where a relevant process variable can be analyzed. interactive features are added that allow users to select the start date and the window size of the visualized data, as well as a drop-down menu to select from a list of relevant operating variables. For those interested, we have released a brief tutorial to demonstrate this visualization with synthetic data. The top heat map shown here is the same as the one on the previous slide, except now the data has been cleaned by removing the shutdowns and other invalid data. The bottom heat map is obtained when we sample the top heat map for extended periods of clean data from all 24 measurements. The extended periods of clean data are then used as experimental trials for developing time series models to forecast the kiln shell temperatures. Note that the largest experimental trial exhibits significant shell temperature variability at approximately 60 feet from the firing end of the kiln. Now that we have visualized the data and prepared it for further analysis, I'll present a brief case study that demonstrates our ongoing work to develop a ring indicator. This figure shows the shell temperature data from the largest experimental trial at the 60-foot position. The red line is the measured data, and it shows some large temperature drops that are not typically characteristic of shell temperature measurements. The blue line is a time series forecast from an autoregressive statistical model. The time series model operates with a moving window such that it produces a forecast with a 6-hour moving horizon. This slide shows the residual generation that was discussed before. The signal presented here is created by simply taking the difference between the forecasts and the measured shell temperatures. Note that the big upward spikes shown in this signal correspond directly to the uncharacteristic downward spike that were observed in the shell temperature measurements. Now that we have generated the residuals, we need to process them into a ring formation indicator. This slide shows two charts that represent the distribution of the temperature residuals in slightly different ways. On the left is a box and whisker plot, and on the right is a simple histogram. We are interested in residuals with large magnitudes, either positive or negative. The largest residual values are circled in orange, and they tend to correspond to problems with the raw data. We need to determine a range from which we can sample residuals that have a large magnitude, but not so large that they are extreme outliers with invalid data. The main takeaway from this slide is that our post-processing for this case study involves sampling residuals from the green circles and avoiding those from the orange circles. Here, I present an example that demonstrates the problem with using the extreme outliers from the temperature residual as ring indicators. This example shows the cause of the uncharacteristically sharp temperature drops observed in the shell temperature measurements. The figure on the left provides a closer view of these temperature drops that become upward spikes in the residual. The figure on the right shows the raw thermal camera images taken from the same period. Note that measurement area G corresponds to the 60-foot position. By validating our residual with the raw images, we can see that these residuals are not indicative of ring growth. Instead, this is an example of an invalid temperature measurement caused by an obstructed camera. This example demonstrates some of the confounding factors that create difficulties with inferring ring growth from shell temperature changes. This slide demonstrates the ring indicator that is developed by sampling significant growth and decay residuals that are not extreme outliers. The figure shown here illustrates one approach to using these significant residuals to create a ring indicator. By sampling from the significant range of positive residuals, we obtain a set of ring growth residuals that span the experimental trial. The same is performed for the significant range of negative residuals to obtain the ring decay residuals. Once these two sets of residuals are sampled, we assign them equal importance by throwing away their magnitude information. Then we generate daily counts from both the growth and decay residuals, which we plot over the experimental trial. The highest daily count of growth indicators is 7, and this occurs twice in consecutive days, which are circled in green. After these 2 days of high growth, we see a day with significant ring decay. Now let's observe this period more closely and use the raw images to try and validate the indicator. Here we see the raw thermal camera images from 4 days in the top figure. Measurement area G is the 60-foot position which we are focusing on for this case study. October 31st is the image on the top left, which is used as a baseline to establish what the kiln shell temperature looked like before the ring growth event. The middle two images are the 2 days of suspected ring growth, and the image on the right corresponds to the day of ring decay. These raw thermal camera images help validate our indicator by confirming that a ring did grow after October 31st, and then it did decay a bit after November 2nd. The bottom figure shows the measured and forecasted kiln shell temperature during these days. The consistent mismatch between the forecast and the measurement, particularly around the beginning of November 2nd, explains the daily indicator count for ring growth. Okay, now I will provide some concluding remarks and some future ambitions. The most significant takeaway I have from this work is that data quality is paramount. Many industrial processes have large quantities of data, but big data is not necessarily good data. Even after cleaning our data, we face problems with extreme residual outliers caused by intermittent camera obstructions. Instead of being able to simply sample the largest residual values, we had to determine a significant and valid range which was around 1.5 times the interquartile range. For future work, we need to finalize the indicator by performing systematic validation across multiple experimental trials. After finalizing the indicator, we can label our data and begin investigating ring diagnosis with supervised learning. We hope to provide an update on ring diagnosis at PACWEST next year. Finally, some references. Here is a list of references, including a link to the visualization tutorial. That concludes my presentation. Thank you for your attention.